Something fundamental shifted in the conversation around humanoid robotics when Elon Musk stood at the World Economic Forum in early 2026 and said, with more precision than he's ever used before, that Tesla expects to be selling humanoid robots to the public by the end of next year, not demonstrating them, not leasing them to select partners, selling them as a consumer product to ordinary people. That statement, measured against where Optimus actually stands today, is either the most consequential product announcement in Tesla's history or the most ambitious timeline any technology company has ever attached to a product as complex. Possibly both. To understand what Musk actually committed to and why the distinction between what he said and what people heard matters enormously, you have to start with what Tesla Bot Gen 3 is and is not at this moment, right now. Optimus robots are operating inside Tesla's own factories, performing tasks that are genuinely useful but that fall well within the category of structured, repetitive industrial work. Moving components, sorting parts, handling logistics within a controlled environment where human movement is predictable, tasks are defined, and risk can be managed systematically. These are meaningful accomplishments for a humanoid robot platform, but they are a long distance from what it means to operate safely and reliably inside a human home. Musk acknowledges this gap directly, and his acknowledgement is actually the most important signal in his entire WEF statement. He laid out a clear sequence. Gen 3 launches as a commercial product this quarter. Throughout 2026, it deploys inside Tesla's factories at scale. By late 2027, if the reliability and safety data from that factory deployment meets Tesla's standards, public sales begin. That sequence is not a delay disguised as a plan. It is a fundamentally different approach to product launch than the tech industry typically uses, and it reflects a genuine understanding of what is at stake when a machine begins operating autonomously in spaces shared with people. The word commercial in Tesla's framing deserves careful examination because it is doing a lot of work that most coverage glosses over. A commercial robot, in Tesla's definition, is one that performs economically valuable work. It justifies its existence through productivity. By that definition, Optimus Gen 3 becomes commercial the moment it starts replacing repetitive labor inside Tesla's manufacturing operations, which is exactly what 2026 represents. But commercial is not the same as consumer. Consumer means a product is ready for the general public, for uncontrolled environments, for the full, unpredictable complexity of human domestic life. Tesla is not claiming that Gen 3 is a consumer product yet. What Musk is saying is that the path from commercial to consumer runs through 2026 factory deployment, and that by late 2027, he expects to have enough data and confidence to cross that threshold. Why does factory deployment matter so much as an intermediate step? Because Tesla's factories will function as the largest real-world testing environment for humanoid robotics that has ever existed. Every Gen 3 robot performing useful work inside Giga Nevada or Giga Texas is simultaneously collecting data about movement balance, object interaction, response to unexpected situations, and long-term mechanical reliability. This data feeds back into the system continuously, allowing Tesla's engineers to identify failure modes, refine motor control algorithms, improve sensor fusion, and validate the durability of every mechanical component under sustained real-world stress. The factory is not just a place where Optimus works. It is the proving ground where Optimus earns a right to enter homes. The new AI5 chip sits at the center of what makes Gen 3 genuinely different from its predecessors, and understanding what the chip actually changes helps clarify why Tesla's confidence in this generation is higher than before. Musk confirmed recently that AI5 chip design is nearly complete, and early work on AI6 has already begun. Tesla is planning chip generations all the way through AI9, operating on roughly 9-month design cycles. To put that in context, the traditional semiconductor industry typically requires 18 to 24 months to move from one chip generation to the next. Tesla is attempting to run that cycle at half the speed and sustain it indefinitely. This is not incremental optimization. It is a fundamentally different philosophy about how hardware should be developed, one that treats chip design with the same iterative velocity that software development normally operates at. For Optimus specifically, the transition from AI4 to AI5 addresses what has historically been the deepest practical limitation of humanoid robots, not raw computational power, but latency. The gap between when a robot perceives something and when it physically responds has been the bottleneck that makes robotic movement look mechanical, hesitant, and unnatural even when the underlying intelligence is sophisticated. AI5 reportedly delivers up to 5 times the memory bandwidth of AI4, which means data moves between memory and processing units dramatically faster, and the robot's physical responses become fluid and continuous rather than calculated and delayed. The practical difference this makes can be understood through something as simple as catching an object thrown toward the robot. With older hardware, catching requires anticipating where the object will be and prepositioning the hand, because the system cannot react quickly enough to track the object in real time and adjust continuously. With AI5's dramatically reduced latency, the robot can calculate the object's trajectory as it moves, adjust arm position dynamically, time the grip closure precisely, and complete the catch with naturalness that older hardware architectures simply cannot produce. Scale that capability up across thousands of physical interactions per day in an environment full of unpredictable human movement. And the difference between AI4 and AI5 becomes a difference between an impressive industrial tool and something that might actually function safely around people. Managing the power and heat implications of a chip that's capable inside a mobile robot is its own engineering challenge, and Tesla has addressed it through the manufacturing process itself. AI5 is being produced on advanced 2-nanometer and 3-nanometer fabrication processes, with Samsung handling 2-nanometer production at U.S.-based facilities and TSMC manufacturing a 3-nanometer variant. These process nodes deliver dramatically better energy efficiency per unit of compute compared to older fabrication technologies, which means Optimus Gen 3 can carry a brain 5 times more powerful than its predecessor while still operating for practical durations without thermal management failures or battery drain that would make real-world deployment impractical. Musk has been explicit about what each successive chip generation is designed to accomplish across Tesla's product ecosystem. AI4 enables full self-driving capability at safety levels significantly above human drivers. AI5 pushes cars toward near-perfect autonomous operation and provides Optimus with the processing capability needed to handle genuinely complex physical interactions. AI6 targets both advanced Optimus capability and data center applications. The same framing applies to child safety applications. An always-alert presence that can supervise, recognize dangerous situations, and respond without the fatigue or distraction that affects human caregivers addresses a real anxiety that parents carry. Musk envisions Optimus handling feeding and monitoring for pet owners as well. These use cases share a common characteristic. They involve trust at a level that goes far beyond what any previous consumer technology has required. A smartphone that malfunctions is an inconvenience. A robot that malfunctions while caring for a child or an elderly person is a potential catastrophe. That asymmetry in the consequences of failure is precisely why the gap between factory deployment and consumer deployment must be crossed carefully, with data rather than optimism. Critics of Musk's timeline raise objections that deserve honest engagement rather than dismissal. Professors and researchers who have spent careers studying humanoid robotics point out that the combination of safety, usefulness, and affordability at consumer scale has never been achieved, and that the engineering challenges involved do not yield simply to faster iteration cycles. Physical intelligence, the ability to understand and appropriately apply force, balance, resistance, and fragility in real-time interactions with unpredictable humans, advances far more slowly than software intelligence. A language model improves through exposure to more text. A robot's understanding of how to handle a fragile elderly person's arm improves through physical experience that cannot be fully simulated and cannot be rushed without accepting risk. Boston Dynamics spent decades refining robotic movement without attempting mass consumer deployment, and that caution reflects genuine understanding of the gap between impressive capability demonstrations and the reliability standards required for unsupervised operation around vulnerable people. Tesla is attempting to cross that gap on a timeline that most robotics researchers consider aggressive to the point of implausibility. What makes the Tesla approach potentially viable despite that skepticism is the data advantage. No other company has Tesla's combination of real-world AI training infrastructure, manufacturing scale, and the ability to deploy thousands of physical robots in controlled environments simultaneously to accelerate the learning process. Whether that advantage is sufficient to compress the timeline to the degree Musk is suggesting is the central unanswered question. What is clear is that Tesla's fundamental design philosophy for Optimus differs from every other humanoid robot program in one critical respect. Most robotics companies start with hardware and add intelligence afterward. Tesla began with intelligence and built hardware around it. Optimus was conceived as an AI system that needed a physical body to interact with the world, rather than as a mechanical system that needed software to make it useful. That inversion changes the development trajectory significantly, because the AI capabilities that underpin Optimus are not being built from scratch for robotics. They're being transferred and adapted from a system that already processes billions of miles of real-world visual and spatial data every year through Tesla's vehicle fleet. The question of whether Tesla is moving responsibly by targeting late 2027 for consumer sales does not have a clean answer. The caution embedded in the factory-first deployment strategy is real and reflects genuine engineering discipline. The timeline itself remains aggressive by any historical standard for consumer robotics. Both things are true simultaneously, and the tension between will define the next 2 years of the Optimus story. What is not in question is that the stakes are higher for this product than for anything Tesla has previously attempted. Humanoid robots operating in human spaces represent a genuinely new category of technology, one where the consequences of getting it wrong extend well beyond disappointed customers or recalled products. Getting it right, on the other hand, could represent the most significant expansion of human capability since the personal computer.